Humanity! I love you all with all my heart and might. I'm Jam Jose Alonso Molina. This video is about truth, the power of truth. This is the message today. As you know, I'm a mathematician, I'm a writer, I'm an author, I'm an entrepreneur. I do all sorts. I'm a programmer, I code, I build apps. I am a philosopher. I speak about governance and I speak about all sorts of things, progress, objective reality, purpose, action, uh, physics. I do all sorts because this is my life. I am a purposeful human being, so I talk about the truth. This is my pursuit. My pursuit has become the truth. So recently I made a video about the Riemann hypothesis, how I solved it. And I solved it using real numbers. I solved it using real analysis, like elementary algebra. Essentially, partial fractions. Like where I live, our curriculum here at school starts teaching partial fractions and algebra in year 9. So that means you're like 14, sometimes 13 years old. And at that age, you're already introduced to this concept of algebra, right? Elementary algebra, partial fractions. And this is real numbers, this is real analysis. This is basic mathematics, elementary, and there is this belief that the complex plane, analytic number theory, complex numbers, imaginary numbers, and all these noise is essentially the mechanism to solve Riemann hypothesis. But this is completely wrong. And my mathematics, which can be downloaded from my website, findingpurpose.co.nz, it's there for free. The paper is fully there. Everything can be testable. Clearly shows that I solved the Riemann hypothesis using elementary algebra. I derived the critical line 0.5 using geometry, the most fundamental way of mathematics, calculating, the space structure itself of the Riemann sphere, right? And I did it using elementary algebra, partial fractions. I didn't have to do any sophisticated complex analysis. I didn't have to do any complex plane to explain the Riemann sphere and then find the critical line that essentially amounts and the magnitude and counts all the primes. So I derived the prime number theorem using geometry, and then I used analytic mathematics, elementary in a way, using algebra. And then after I derived it, 0.5 as the pole, S, if you think in terms of Riemann hypothesis, but in reality, S is just the pole. It's the critical line, 0.5, 1 divided by 2. And I did that in one-dimensional line using the specific requirements of the hypothesis, using the rules of the plane, of the complex plane. Right? But I solved it in the most elegant and simplest of ways, which is using elementary algebra. And then once I found it, I found the critical line, right? Then you have to test it, right? Because, okay, so the algebra is clear. I found the critical line with the operators 1 and 0. So then I have to test it. And how do you test it? Well, you use calculus, right? It doesn't have to be complex. It has to be just elementary calculus. And for that, you use convergence. You use tests. You use sets. You use domains and codomains, right? You use real analysis. So you can essentially find the limits, right? And understand whether, in fact, when you apply this to geometry infinitely, in terms of the Riemann sphere, which is just a regular sphere, once you understand what it is, the critical line and the poles, then you start to realize that, well, the limits, are there. It starts at 2 as integrals, right? When you do the convergence and you have integrals, right? The working calculus, which is fundamental to making sure that the algebra and the partial fractions actually, check out, then you start to immediately realize that, yes, in fact, it's 0.5. And in fact, it cannot be any other number. It has to be 0.5. It has to be 1 divided by 2. It cannot be anything else. Otherwise, it doesn't work. This is why in 167 years of, people trying to use the complex plane, analytic number theory to find the answer, they haven't. Because what they've been doing is they've been calculating noise, a monopole error, as it's called in mathematics, which is essentially they're just calculating linearity. So they're going in a linear path, calculating to infinity, trying to find the zeta zeros in a line that will never give it, because they're only identifying the noise on the surface of the sphere. Because in the beginning, the problem was that Riemann thought of the sphere and the poles of the sphere, 0, 1, -1, and infinity, as points on the surface of the sphere, which is incorrect. Because how can you find the critical line on the surface of the sphere if the sphere is a geometry? I understand that in the plane, in the complex plane, you're thinking in one dimension, which is the linear dimension of the plane. But then instead, you got to understand what the volume of that line itself is, of that dimension. And to calculate that, well, you use the sigma function, which is part of the Riemann hypothesis itself. He himself used that to formulate the hypothesis in his work. He used the sigma function to indicate the space itself that contains the zeta zeros for the work. So when you understand this idea, then you understand that, well, when he makes reference to the Riemann sphere, he's making reference to the sigma function space of the zeta zeros, the surface of that space. Yes, that's where the primes are, but that is not where the critical line is. But remember, he said that in order for us to account for the zeros, we need to identify the critical line, which is 0.5, as he correctly identified for the first few magnitudes. What he did the work manually such a long time ago. So then you understand, if this is the hypothesis, then how can we actually understand the magnitude? Because you got to understand, as a logician and as a mathematician, as a pure mathematician using real numbers, that he already found the answer, but he didn't fully prove it. That's why it's a hypothesis, because he believes it's 0.5, because he identified that in the first few sets that he calculated, right? But then if you understand that idea and you understand the power of what he meant, he did that by using the sigma function. So then you understand, well, what is it that allows us to measure things? Because remember, what are we trying to measure? Well, we're trying to measure the prime number theorem. We're trying to have an exact number of primes, counting primes at any given magnitude. Meaning any number will give us the immediate number, the total number of primes contained within that magnitude. So then if you think in terms of linearity, one dimension, as he did using the sigma function that equates to 2 in the end, then that's why when you think in terms of integrals, what's the first prime number? Well, the first prime number is 2. So that's why the integral starts at 2, as in terms of the lower bound. And then the upper bound is infinity itself, right? That's why you need to count to infinity, which is how can you do that to infinity and always get the same result? Well, you need the prime number theorem, but the way they calculated it with Gauss and all that, who was Riemann's mentor, was using approximation, right? It was an approximation, the theorem itself, that would kind of help them but it wasn't precise, right? It wasn't but they used the sigma function to develop that theorem in terms of so that's how Riemann found the critical line for the first few numbers, but it wasn't a law per se, because he didn't fully prove it. And that's why the hypothesis has been so relevant, right? Because everything requires prime numbers. If you think in terms of computing, software, hardware, advanced manufacturing, and everything that we do in the modern world requires prime numbers, right? So then that became the quest. The quest over time became, well, let's find the critical line. But because he developed that in the complex plane, people assumed that the answer was in the complex plane. Because at the time, the complex plane was a thing. He said, well, we cannot really deal with infinity in simple terms, in real terms. We need to think in complex terms, imaginary numbers, to assume everything so we can find the zeta zeros on the surface of the Riemann sphere. Right? So that was the assumption at the time, but that was actually, in fact, incorrect. Because if you understand measurement from a geometric point of view, which is mathematics, and this is basic mathematics, you cannot know the volume of something unless you know its dimension. So you need to know what the space in which that volume is held, contained, so you can then understand its magnitude. You can then understand and measure it. So by understanding its space, its topology, its geometry, mathematically speaking, then you will be able to count its space. And by counting its space, then guess what? You can derive geometrically, analytically, and elementary the prime number theorem. Because the prime numbers are contained within the integral. And the integral is that law, right? That essentially is the foundation of this entire branch of mathematics, right? Which is the foundation of number theory. So if you understand this, then you understand that, well, if the integral starts at 2, because otherwise if you start with the operators 1 and 0, the integral collapses because 0 is undefined, right? Mathematically speaking, because you cannot divide by nothing. Then it becomes a conundrum, right? Like, well, that's the puzzle. Is, well, where is the critical line then? Because we have been seeking the critical line, as S, thinking that S equals 1 in terms of the pole in the surface of the sphere, which is all the numbers, all the prime numbers, starting at 2 with the integrals and the sigma function and all that. So the volume and the linearity of that dimension essentially became the quest of finding something that will never be found in that space because it's not contained within its surface. It's contained within its space structure itself. That originates it in the first place, which is the operators 1 and 0. Because if you understand mathematics, you understand that the only two numbers outside the integral are 1 and 2 as operators, because the integral starts as the lower bound at 2, which is the first prime number, because this is number theory. This is the prime number theorem. We're counting primes, meaning we start with the first prime, because once you understand the first prime and you understand what primes are, then you can understand what the composites are, which is essentially what allows you to understand these at length. Because when you know the primes, then you know the composites. And by knowing the composites, then you know the difference, and you can account for the entire space, the entire volume of that Riemann sphere in that volume, in that space. And by doing that, then you know the difference, so you will know exactly how many primes exist in that specific magnitude. If you understand volumetric analysis, geometrically speaking and topologically speaking, right? But they never did that. They never understood that. So they were seeking within the integrals. They were seeking within the zeta zeros, the critical lines inside the noise of the surface of the sphere. But in reality, they should have started prior. What is it that creates the integral in the first place? Well, it's the critical line, it's the 0, right? The zeta zeros that allows the spacing and the distribution, the gaps for the primes. So the prime number theorem can actually account for them, so you can know the difference between the composites and the primes. So if you understand that geometrically speaking, then you got to understand that there is no difference between the Riemann sphere and a regular sphere. They are the same. But one is a complex analysis in terms of the linearity of the one dimension of the sigma function applied to the integral starting at number 2, and the other one is just a regular sphere, a traditional sphere as we all know it. So then what you do? Well, how do you find the critical line? Because it is the critical line that allows us to count the primes in the first place, which is the hypothesis of Riemann. So then you got to understand, well, if it's not within 2 because we haven't found it, then it has to be prior to that, meaning what creates it? Well, the only thing that creates 2 is 1. because it's the operator outside the integral itself. Because if you add 1 and 0 and try to start the integral within as 1 and 0, then it collapses and you cannot account for infinity because it's not measurable. Meaning you cannot divide by 0, it's undefined. Mathematically speaking, it's not standard mathematics, which is what we're doing. So then what do? Well, we find S, right, as X, right? So how do we find S as X in terms of how do we find the pole, the critical line, 1 divided by 2, which is 0.5. So we can then account for the measurement and the volume of this Riemann sphere and the complex plane and the prime number theorem and everything, so we can prime count at any magnitude. Well, we define X equals 0 because it's the first operator. And we do this using elementary algebra, and this is part of my work, which is all published, right? So if you understand that, well, when X equals 0, and then, because you got to understand this, why am I equating X to 0, meaning S as a pole? Because I'm trying to account for the first two operators, right? Which are 0 and 1, which are outside the integral itself, which is the prime number theorem that starts there to account for all primes, which starts at 2, as we know, as a lower bound. So then it gives infinity itself, geometry itself, gives us the first clue, which is 2. It's telling us the first prime number is 2. So you need to account for 2. Okay, so that's good because it's the beginning, remember. So what came before the beginning? Well, it was what created 2. And what created 2? Well, 1 and 0 as operators. But you got to understand the meaning of that, which is what I'm going to explain next. So you understand the first clue of nature, the first law of mathematics, which is that integrals start at 2 because the lower bound needs to be 2 because it's the first prime number. Otherwise, you cannot hold it. Okay, great. So it's telling us it's 2. This is a hint. It's 2. That's a clue. And then the second clue is the fact that when Riemann defined his hypothesis and he developed it, he used the sigma function, which is something that Gauss used as well, but he applied it to the context of the complex plane, and then he defined it in a way in which it equated to 2. So the volume of the line, meaning the volume of the one dimension, equals 2 in the end once you do the calculations, as I've proven in my work, that you can check easily. So because of the sigma function and the importance and the relevance of the sigma function within the space structure itself of the complex plane where the zeta zeros are supposed to be found. So he used that, and when he calculated that, he found the critical line for a few magnitudes for 0.5, 1 divided by 2, which is what led him to believe that the pole was there. All the zeta poles have to be in alignment with that, with the critical line, for us to be able to count primes to infinity at any magnitude. So then that's the second the second clue. The second clue, which is the second, like the other face of the coin, the two sides of the coin, you needed to confirm why is it that the first prime number is 2. Well, and that's what Riemann gave us, but he didn't understand it at the time what he was doing because he was too focused on the analytic number theory side of things, the complex plane, the complex numbers, rather than thinking in real numbers terms, which is the volumetric value of the integral itself starting at 2. So he went the way around. He thought the Riemann sphere was 0, 1, minus 1, and infinity, thinking in terms of that's where we're going to find the zeros on the surface of it, right? Because it's linearity. But in reality, it was the opposite. You need to find it at the epicenter of it, at the center, which is its geometry. So you understand it. So that's where it was, because that's why he couldn't account for all the zeta zeros and he saw so much noise and so many things that were imaginary that became extremely complex and too many assumptions, and it became just essentially noise and bias, if you understand what I mean. So then, okay, so what's the second 2? Well, the second 2 is provided by this sigma function itself. When you understand geometry, and what is geometry of the sphere? Well, it's given by the root of pi. So when you start to do the calculations and you do the transformation, then you start to see that the complex analysis itself, which is the inverted, of what he did, then it gives you 2 as well. Oh, okay, so the volume of the plane itself is 2 equals 2. So, well, that makes sense, because if it starts at 2, where the first prime number is, then it means that if it starts there, the volume has to be complete, right, of that Riemann sphere, because it starts there, because you cannot account something without volume, without geometry, without topology. So its topology starts at 2, which is the prime number, right, as the integral says. And then it says that the volume is 2 when you apply it to sigma function of pi, using the same transformation, using the same conversion and inversion, using his own sigma function for S. Then you start to realize, oh, okay, so the volume is 2, which means that the first prime number is 2. So we need to look at number 2. So if you want to, because my objective became, well, how do I find the critical line using real numbers, real analysis, using elementary algebra, elementary calculus, simple and elegant, so I can prove it geometrically and derive it, right, using the same principles. Well, S equals 1, right, according to his analysis, right? But S is just X, if you understand the plane. So then the operators 1 and 0 outside the integral. So then what creates the volume? Well, it has to be the operators, which give us the critical line, which is 0.5. So when you transform Riemann's S into a isotropic quadratic form, why quadratic? Because it has to be 2, because of the volume and the first prime number being 2. So that's the clue. And you're transforming the same space. So you're transforming S into a isotropic quadratic form. Why is it isotropic? Because it's a sphere, it's a Riemann sphere, and all the zeta zeros has to be in alignment. And the alignment is 0.5, which is the critical line, 1 divided by 2. So because it's that, and everyone has to be the same, according to the hypothesis, then it means that it has to be isotropic. So the space structure itself of that complex plane, where the zeta zeros live, which allows us to account for the prime number theorem, so we can count any primes to infinity and any magnitude, then it tells us right there that S has to be quadratic and isotropic, meaning it applies the same space structure and distribution across all points, all vectors. That's why it's isotropic. So it's isotropic quadratic form, which is a standard mathematic work, right? A term. So if you understand that, then, well, you transform it, because you're seeking, what are you trying to find? The critical line, the zeta zeros, right? The poles. But if they're not within the integral, which starts at 2, lower bound, because we haven't found it, then it has to be outside of it. And the only two numbers that are outside 2, what are? Well, 0 and 1. So then you allocate X as the quadratic form, the isotropic quadratic form, is an equivalent of S as a pole. So you start X equals 0, and you do partial fractions with the transformation of the isotropic quadratic form, and you apply that to algebra, regular algebra, elementary algebra. And then when you do the calculation for X equals 0, then guess what the answer is? Well, the answer is -1. Well, right there, -1 is the polarity, right? You understand? It's part of the surface. If you account for Riemann sphere, then it's telling you, hey, there's something here, because the Riemann sphere, the poles of it is 0, -1, 1, and infinity. So if you do that isotropic calculation based on the sigma function, which equals 2 in terms of volume, and then the integral starts at 2 because 2 is the first prime number, then the mathematics of that quadratic result using algebra is telling you that X equals 0, meaning that when the quadratic X is 0 and you apply it to the form, which is isotropic, that applies to the volume and the topology and the geometry of the sphere, which is what I did with the transformation. You can review the paper. Then it gives you -1. Well, that's a sign, right? -1. Why is it -1? Okay, so then let's do it for -1 then. So X equals -1. So when you calculate it for -1 as X, then guess what the answer is? After you do the isotropic quadratic transformation, like the form, you did the whole lot. Well, it's 0.5. That's not a coincidence in algebra. How is it that it's 0.5 for minus 1? Because we started with 0, which is the first number, right? In terms of computers, which is what we're doing, because computers require primes, right? So then, if you start with, because when you think in terms of binary, which is the way computers think, what's the first number of computers? 0. Now 1 is 0. Is how it starts. They start counting as 0, 1, 2, 3, and they go to infinity, right? Well, so you start with 0 because computers thinking, we're trying to think in computer terms here, right? Mathematically speaking, using pure mathematics, so then it can be applied to applied mathematics. So when you start with 0, which is the first operator, then it gives you minus 1. So then it's a hint. So well, you calculate x equals minus 1, and when you do that, guess what? It gives you 0.5, which is the critical line. And I'm like, okay, well, this cannot be a coincidence. So if minus 1 is that, and the Riemann sphere is 0, minus 1, and 1, then naturally you need to calculate 1. And when you calculate 1, x equals 1, using the isotropic quadratic form, guess what the answer is? 0.5 again, which is the critical line, 1 divided by 2. And then if you do basic arithmetic, you take minus 1 plus 0.5 plus 0.5, which is essentially minus 1 plus, all the other two, 0 and 1. What is the answer? It's 0, meaning the beginning, the balance, right? So you can have a balanced state because 0 is not undefined in that space because the critical line is 0.5, which is the weight of that dimension of the volume, because you found it with the operators 1 and 2, which is what allows for the integral to be 2 in the first place, which is the first prime number, so you can account to infinity. So I found the critical line using partial fractions, using elementary algebra, taught in high school level stuff. Because no one was looking for it, I was able to find it because I understood that in order for you to measure the magnitudes, meaning the total count of prime numbers, you need to understand its volume, its base. And the hint is that it's 2. It has to be within 2 because 2 is a fair prime number, and then the volume of the sigma function happens to be 2. And when you apply it to pi, which is a sphere, then it gives you that. So, and then when you start to do that, then immediately you start to then, obviously, so if the answer is telling me that it's precisely 0.5, right, for its topology and geometry and its scale, using pi and using the rational numbers, transcendental the rational numbers pi and phi, which are the dimensions that nature uses itself to account to infinity, creation space, topology, right? This is being proven by Fibonacci. This has been proven by Euclid and Archimedes long ago, right? So when you apply it to real, geometry and topology using real numbers, then immediately you start to do analysis. Well, let's make sure that this arithmetic that is in balance, that is giving us this result, that is telling us that the critical line is in fact 0.5, right? Because then you can divide by 0.5, which is, it's the pole. Because then you apply sigma, then you apply everything, and it's 0.5. And everything is in the work. But then you do the analysis, right? You do the convergence, you do the integrals work, you do everything. You do the sets, you do the domains, codomains, you do the real analysis. You do everything that you can do mathematically using real numbers, using, and applying imaginary numbers as well and everything. And then it calculates it to infinity, and it does it, and, it's 0.5. So I solved it. I solved it using actually, real numbers. Real number theory, like not the complex plane. So then that accounts for that. And then when you start to keep on doing the analysis, then, well, you need to account for the imaginary numbers to make sure that, because why is it there is so much noise in the infinite space of the surface of the Riemann sphere when you think of it as the poles being on the surface rather than its center, which is 0.5, right? So it accounts for the numbers, right? And then you find a way. And I'm going to explain to you visually why it has to be 0.5. So, for example, think of a sphere, right? So you have a sphere, right? And this is the weight of it. Think of it as the pole of the sphere, right? So you got the weight, which is a critical line. So the stability can exist in that geometric space, in that topology, in that volumetric thing that you're trying to account for, so you can count the primes. So think of this as this weight, right? And then think of this sphere, which is lighter, because this is wood, a wooden sphere, and this is a metal sphere. So when you have, say, imbalance, then it's not going to be the right way, because say, for example, if you take any operator, say x equals 1, and the result is different from -1 in terms of like, and then you calculate it for -1 and it gives you 0.5, and then you do it for 1 and it gives you 0.5, it means that -1 plus 1 equals 0, right? It's imbalance, which is what you need, right? Because you're seeking the zeta zeros. So it's giving you the answer that are there, but by the critical line, which is 0.5. Because of the balance, -1 plus 0.5 plus 0.5 equals 0. Why does it have to be 0.5 for -1 and 1? Because it will be the same weight, 0.5. So if you have a lighter thing, which is not 0.5, and a heavier thing, which is not 0.5 or 0.5, then they don't match because they're not in equilibrium. So the sphere collapses because, as you know, geometry needs to be isotropic in terms of the sphere for it to hold. So this doesn't work. So it needs to be zero. Both spheres needs to be the same weight and exactly the same. So it accounts. So it cancels out. So you can account for the noise and you can account for everything, meaning imaginary numbers and everything within it. So everything in mathematics is contained within it, which is the only way it would actually work. That's why x equals 0, which is s essentially, gives us -1, right? When you do the isotropic quadratic form. And when you have the calculation for -1, then it gives you 0.5, which is one weight of the equation, right? But you need 2 because -1 is its counterpart, which is 1, which is what S1 is, the pole. So when you calculate x equals 1, and then it's the same 0.5, then you got the balance because the weight is 0.5 for both. So you found the balance. You see, it's not 0. You're not dividing by 0, right? You're not dividing by 0 because it's undefined. But you're using 0 to find -1, which is what creates that volume, right? That polarity. So it keeps the balance, the beginning of it, of the sphere, of the geometry, the vacuum that creates the space, a spherical vacuum threshold. And when you calculate S1, then it gives you this critical point, which is critical line, which is 0.5, which is not 0. You can divide by 0.5 in terms of sigma, right? Which is the whole purpose of the Riemann hypothesis. And then when you then do the opposite of -1, so it's a counterbalance because you have to, because 1 is the first operator outside the integral for the mathematical law discovered by Gauss, and when he designed all that work, so Riemann created the hypothesis itself for the prime number theorem. So then it gives you -0.5 as well, which is not 0, so it can be divided by as a critical line, so you can find the zeta zeros. And when you account for the -1 plus 0.5 and 0.5, then you get 0, which is a zeta zero. So the zeta zero is sitting on the critical line, which is 0.5. And it accounts to infinity. And that's what it works, you see? So, and then when you apply that geometrically, right, you solve the complex plane. And then if you really want to test that, you know, the real analysis, well, you do the complex analysis. And when you do the complex analysis, then you start to realize that using the same principles and the same concepts, because, you know, mathematics, the reason why pure mathematics is pure is because it's honest. It tells the truth. It is actually fact or is not, and you do the calculation and review. And because the algebra is so precise and the arithmetic is precise, the arithmetic, when you do -1 plus 0.5 plus 0.5 equals 0, which is a zeta zero, right? The pole, which is a critical line, 0.5. accounted for and in balance, right? So you can have an isotropic geometry, which is the Riemann sphere. Then when you have that, then the arithmetic, which is the most basic mathematical law, tells you, hey, it accounts for it at all levels. It's in balance. It's perfect. So do the next level, which is algebra. And when you do algebra and partial fractions for it, then it gives you the same calculation because it was the derivation of the algebra that allowed me to do the basic arithmetic afterwards. But I needed to do the analysis of algebra using the quadratic transformation, right? And then when you do the algebra, then mathematics, because it's pure, it pushes you to the next level, which is calculus. Because you need to go beyond algebra. You need to go into calculus to make sure that the motions of the sphere and the topology and everything is actually coherent and it works and it holds at any level and scale of infinity, at any magnitude. And when you do that, then exactly the same, it holds. How is it? And it's not like there's no margin or error. It's zero error. It's perfect. It's precision. It's 100%. It is what it is. The truth. It is that Riemann was right. There is a hypothesis which is correct, which I've proven, which is that the critical line of the zeta zeros is 0.5, meaning 1 divided by 2. And it exists, and it is the way it is. And that's the law of nature when it comes to mathematical thinking in terms of the prime number theorem, because then as a result of that, I was able to do all sorts of work, and then, which is all my work, so I derived the prime number theorem geometrically to have the precise magnitude at any scale, so you can count prime numbers to any scale using the complex plane. And because you do that,